Our today's topic of discussion is the continuity equation in electrostatics. So for that purpose we have considered a differential volume which is having volume charge density rho v, and we know that the current can be written as rate of flow of positive charge. We can write like that, and according to the continuity equation, if we wish to define this, then we can say that the amount of electric charge in any differential volume of a space can only change by the amount of electric current flowing into or out of the volume. Okay, otherwise it will remains conserved. So in another way we can say that the continuity equations tell about the conservation of charge as well. So we can write it is another way to say conservation of charge. Okay, concentrate at this point. If current is flowing outward from this differential volume, okay, then the current is flowing outward, then the inside concentration of charge is reduced, as the current is nothing but flow of the charge. So if positive charge, if current is moving outward, it means the positive charges are moving outward, and inside the concentration of charges are reduced. As the charge is flowing outward, the concentration of the charge inside reduces, so the rate of change of charge can be negative due to the reduction in the concentration inside. So we can write d over dt. Q for this differential volume can be written as rho v dv, and for full surface, for full volume, it can be written as volume integral. So this is the current. It can be further written as, this is simple operator, so we can take it inside as well. So we will take volume integral outside, d over dt rho v dv. We can write like this, and the current can be written as the surface integral of current density over closed surface. So according to that, this current can be further written as the surface integral of current density into surface integral of current density over closed surface ds. Okay, we can write like this, and if we will try to relate this with the divergence theorem, then from there we can say it can be further written as the surface integral of j dot ds can be transformed into volume integral, and that is the divergence of the vector. So this is the divergence theorem, and if we define this, then we can say it is the volume integral of the divergence of vector field J taken over entire volume is equal to the surface integral of the field over the closed surface surrounding the volume. So in this way we can write the divergence theorem. This we have studied already. Okay, so no need to concentrate it again. And if we relate equation, this is first equation, this is second, and this is third. And if we relate equation 2 and 3, then we can say volume integral minus our entire volume d over dt rho v volume integral dv can be equal to the divergence of j dv. Exactly, we can write like this, and as it is signed we can take it inside, so it can be minus without any change. Now if we relate this and this, then we can say divergence of current density J can be equal to the minus d over dt rho v. This is our continuity equation. So the rate of change of charge density is negative. Okay, consider a case, for example, in a closed circuit when you are applying KCL, then what's about charge? It remains constant. Okay, just it is following the path, closed path, however it remains same in the circuit. Okay, so if charge remains constant, then del rho v over del t can be equal to the 0. In that case, divergence of current density can be equal to the 0. So what we can say regarding this, that is applied in KCL. In a closed circuit, the charge remains constant, that is according to KCL, and the divergence of the current density will be equal to the 0. In that case, if divergence is 0, means J is solenoidal. So we can write, if divergence of J is 0, it means J is solenoidal, or we can say it is conservative. Okay, and in continuation of the topic, if we can say the divergence of J can be written as over dt. Okay, for time being, if we consider absolute value of this, then we can say is equal to rho v over dt. This is the divergence which will give you the del j over del x plus del j over del y plus del j over del z. If the current is moving in 1D, so if we consider the single 1D dimension, then we can say dj over dx. Okay, consider in the change in the x direction. Then we can say rho v over dt, and it can be further written as dj is equal to d rho v over dt into dx. So it can be written as rho v into dx over dt. We can write like that. And what is this, by the way? If we write J, that is current density, then we can write rho v into dx over dt. What is this? This is velocity, that is named as Vd. And what is, if you are finding for full J, then you will be rho v. This is named as drift velocity. I think you all are familiar from the drift velocity, so no need to discuss it here again. And rho v can be written as the number of free electrons, that is Ne. So J further can be modified as N E V D. Okay, so this is the final term that can be written regarding the current density J. And Vd can be written as, it is proportional to the E. It is the net drift in the electron in the field. So that is proportional to the field, linear proportional. Okay, and if we remove the proportionality, then it can be replaced by mobility of the medium. Okay, and mobility you can, okay, note down mobility. And this can be defined as the ease of flow of charge. Okay, so in this way, replace J from here, N E mobility E, and J, this term is further defined, that is conductivity. So you can say this is conductivity. Okay, and conductivity is nothing Ne mu. In the case of perfect conductor, conductivity is infinite, as mobility, ease of flow of charge is infinite. So the conductivity will be infinite in case of perfect conductor. Okay, so E can be written as J by sigma from here. In case of perfect conductor, that will be equal to the 0. Okay, so in this way we can say the electric field inside a conductor is 0. Okay, and in reverse direction, if it is perfect insulator, then the conductivity will be 0 and the current density will be 0, because 0 times E will be, J will be equal to the 0. Okay, so what we can say, the divergence of the current density is 0 if rho v is constant according to KCL, and J is equal to sigma E. Okay, and J divergence of current density will be minus of T rho v if the charge is flowing, the concentration is changing. So these are the derived terms from today's lecture. So hope until this point the things are clear to everyone.